Okay guys, I think we are live once again. Let me check again what's going on. Okay, all things is excellent. We are live now. Okay, so previously we are facing some issues related to live streaming, and I think we are live now. Okay, I get notification. Okay, actually what's happening now, when I schedule the live stream for 5 p.m. and then we didn't live that time, so that's why we are facing issue right now. So I think quality is clear, everything is crystal clear. Okay, so welcome to Bits and Bytes, guys. And right now, okay, let me refresh the comment. Okay, what is happening? It's facing again. Okay, I'm facing some issues right now. Okay, let me open another tab related to audio is clear, I think. And just wait 1 second, guys. We are again facing some issues related to live stream. Okay, we are live now. Okay, thank you so much. Thank you so much for. Okay, we are live now and we have one view right now. So I'm popping out the chat window and shift it to another tab related to this. Okay, I think we are all fixed, so let's start. So previously we constructed the previous video we are writing some codes of principal component analysis, and I want to quickly explain you what exactly a principal component analysis. So let me tell you a definition of it. Principal component analysis is nothing but a technique used for reducing dimensions in the data set. And so what is the use of that dimensionally reduction? Why we use dimensionally reduction? So if you know already why we use dimensionality, let me tell you. If you don't know, dimensionality reduction will drastically increase your training time but loses your training data. That's it. For example, if you want to if you don't have enough power, you don't have enough computing power for training the model, or you don't want to parallelize the training instances or training set, so what you can do is you can use the technique called principal component analysis too. reduce the dimension of the data. So right now I think no one is watching us. Okay. So what principal component analysis do? So for a sake of simplicity, I just want to tell you the principal component analysis just project the data set of n dimension to the subset where the into subsequent subdimension of n dimension. If you are not understanding what I'm saying, let me show you. So okay, I don't have any paint. Okay, let me illustrate, not illustrate, let me tell. And okay, what principal component, if okay, you have a data set of n dimension. Okay, you have a data set of m dimension. For example, in this the number of columns is 30, so there is 30 dimensions. And for if you apply or something, for example, if you apply the training algorithm, for example gradient descent, in this case if you apply the dimension, it will eat up a lot of your training time. And so there will be a as you can see here, so here we have a 30 dimension in our data set. So what principal component analysis will do, it will project these 30 dimensions into the subspace of n dimensions, means in this case is 30. So for example, if I want to project the 30 dimension into 2 dimension, then this all training data can be reduced to 2 dimension, just 2 dimension, and can be visualized to 2 dimension. Let me show you a window, or let me show you a graph of not a graph, it's actually scatter plot of this breast cancer data set, and which where I projected the 30 dimension data into 2 dimension. And it's actually dimensionality reduction is also used for visualization. So actually data visualization give you a strong insight how the clusters is formed, what type of cluster is making in that data set. Let me show you scatter plot of this data. And okay, so let me add a window related to that. So it's all black out right now. Okay, this is the what's actually, let me, okay, I think it's okay. Let me resize this. So here I just projected the breast cancer data of category class 2 here you have two classes, which one first one is yellow and second one is uh, purple, and then we projected the 30 dimension into 2 dimension, and here you can see how this is what we say scatter, how two clusters of breast cancer data is formed. So as you can see, and if you want to apply this if you want to train this data of, for example, you want to train a logistic regression algorithm, in that data it will be a much faster than the more complicated algorithm, machine learning algorithm. So I think it's a very good technique if you don't have a massive amount of computing power. So again we are, I think it's all black. Oh, okay, we are back, and let me show you what's live. We are live streaming or not, what's going on here actually. Okay, okay, fine, it's streaming, I think. So streaming, I think. So okay, so here I apply the same principal component analysis in what we say MNIST dataset, and so here let me reconnect the collab. Okay, now we are in full screen right now. So I imported the data itself from sklearn dataset library, and here it's the 7000 images of handwritten digit of 28 by 28 pixels, and the third line here I imported the matplotlib to print these pixels to sorry, to get the inside of the individual instances. And as you can see here, I picked a random value, which not a random, it's actually 36,000 instance value, and I convert and I reshape that into a 28 by 28 grid, and then I showed it to matplotlib. So between this thing I have done a lot of analysis, lot of classification problem, which is not our agenda of today. What our agenda is actually how we reduce the dimensions of this data, how we can reduce the dimension of this data to increase the time, not to decrease the time, sorry, it's decrease the time to for this data set to train. So here is the cross validation, don't look at it. we'll talk about later. What is the F1 score, we'll talk about later. So here I imported the class called principal component analysis, and from the package called sklearn.decomposition, which is nothing but a singular value decomposition itself. And what is, if you don't know what is singular value decomposition, I want to quickly tell you that singular value decomposition nothing but a matrix factorization. And what it will do, that it will factor into a matrix into a 3 subsequent matrix. What are these subsequent matrix? We'll talk about that later, but for the sake of simplicity, you have to remember just the last matrix, which is a, let me tell you the subsequent matrix first. First one is a U matrix, second one is sigma matrix, which is also called a singular value matrix, which is a diagonal matrix, and third one is V transpose, where U and V both are unitary matrix. Unitary means if we multiply both, if we dot product both matrix U and V, if we dot product that U and V matrix, and then it will be an identity matrix, because both matrices are orthogonal to each other. So what actually orthogonal means, we'll talk that later. For now, you have to concentrate on this particular code. And so here I imported the PCA class, and it need a constructor which is an component, which I will tell you in a bit. And then we fit transformed our data, and then we inverse transform that data using the PCA. So let me show you. So what PCA will do, let me tell quickly what PCA will do. It's actually project your data into subspace of that particular dimension. And so here we tell here in the constructor and component, we tell that in order to oh sorry, I still confuses. Okay, now here we start again. So what PCA will do, it will project the training instances into subsequent subset, and in order to maximize the variance. So if you projected data have the variance which is approximately equal to the original data itself, and that will be a no loss of, almost zero loss of information. We'll lose approximately zero variance. So here we tell that we want just a 70% of the variance on, means this principal component, this projection only wants a 70% of the variance which is inherent from the original data set. So actually the N component is little bit a different thing, and here I showed you a different thing. Actually here I provided is just a ratio of that thing. What if if I just want to preserve the 95% of the data, then 95% of the variance I want to preserve the 95 of the variance, then I uh, then I then I typed then I insert 0.95 of that data. Okay, so after I just after I initialize the object of this PCA principal component analysis, and this object I can use this object to call the subsequent class function related to that principal component. And one of the main function and one of the important functions in the scikit-learn is the fit transform. What it will do, that it will fit the data and transform it in right there, and it will return the transformed data, and we stored that in reduced x, and here is the reduced x. If I execute it, if let me just quickly want it to reduced x dot shape, quickly execute that, and what it will do, let me show you what it actually do. So it's loading right now. So okay, so if we pass the 0.95, it means if we want to preserve the variance of 95%, and after reducing the data using the fit transform, our data became just 154 dimension instead of 728, reduced to just, our data is reduced to just 154 dimensions. And it's a good practice to reduce the data as much as you can, but at the same time you have to remember, you have to take care of the variability of the data and the loss of information. And so if you are thinking to just printing the same 154 the data into what we called something into a matplotlib, so we can do that because we want our data in the 2D form, which is, and if we choose, so let me show you. Before we have a 728 grid and pixels of a grid of a pixel, and it's a 28 by 28, but it's a 700 is the root of 28 because we want a square image, and so here we don't have a 154 images pixels. And what is the root of 154? If we calculate, which is not a integer, which is not a count or what we say integer value, So we cannot project cannot when cannot show here in the image form. What we will do, we will provide the n component approximately 144, so we can project. So if I quickly, okay, what's the problem, if I quickly run this and try to show in the matplotlib, so we get an error right now. So what is the error? Okay, it's not a 12 by 12. Here we get something completely jargon. So it's actually completely bullshit what it's going on. So what here going on? So see, we reduce the data. Here we reduce the data, but to get back the original form means here actually what actually a pixel of how image is formed. We have to understand how image is formed before understand what's going on here. So how images form? Images is nothing but a grid of pixels, and each pixels is a value between each pixel have a 3 channels. In this case we only have a 1 channel because which is a grayscale, and if we have a 3 channel, then what is the name of 3 channel, which is RGB, means a red, green, blue. So in this case we only have a 1 channel. So what where the one in grayscale, the each pixel has a value between 0 to 255, which is total of 256 values, and each value represent the intensity of the intensity of what do we say, black, which is gray, not intensity of a black. And if our pixel value is what we say a 0, and if our pixel value is near to 0, it will be a white pixel, and it will be a completely black pixel. And if our pixel value is near to 255, here we will get a white pixel. So in this case, this traffic transform just arbitrary altered the training instance, each instances, into their own mathematical way, such that it will become something garbage. It became something garbage. So what we have to do before showing the image, we have to reconstruct the image from that parameter it is learned from that fit transform. So what we'll do is we try to reconstruct. So I will do not reduced, it's reconstructed. This is reconstructed, and we'll use the same object and we'll turn to inverse transformers of what? Of reduced x. Okay, let me show you. comments. Okay, what's going on? Oh, sorry, here I'm facing some issues related to. Okay, I think we are fine. I think, let me check again. We are live. Okay, we're live. So what's happening here? We inverse transform the reduced X images, and then we will it will become a n dimension, because we don't want our image to reduce, we want our same data. So if we want to what we say, the reconstructed, if you want to, let me show you a reconstructed image. Here is, and which is a 28 by 28, and here also I think, okay, it's not defined, we haven't run yet. And then this, let me copy this to show the original of that particular image. Here we got the reduced image. As you can see here, when we haven't lost any information, not very much information actually, in this reconstructed image. So as you can see, let me show you original one, which is of X and of 28 by 28. Okay, this is the original one. This is purely what we say white pixel around it, and you have some gray pixel around. So what's happening here? So firstly, the white pixel of 255 value is somewhere projected to near its gray value, to such that to speed up the training. So here we can see our handwritten digit, and around it is the importance, actually it's importance of a pixels. So as you can see, these pixels which have some variation, have some is more important than the pixel around it. And this is the basic fundamental of singular value decomposition, is that it will arrange the matrix, it will factorize the matrix such that the first column is more important than the second one, and the second is more important than third one, and so on. And so that is the basic fundamental of it. Will arrange the subsequent pixel values, will subsequent the vector, it will arrange the vector in such that the one which is previous one is more important than the current one. Previous one means the first is more important than current. So here is the basic general idea of the principal component analysis itself. And you can see if we quickly run pca.in component, will take that of 144 component. So if we want to preserve approximately the 99% of data, so let me show you. Preserve the 99% of variance in the data set. So here I converted will the components of okay, here is the 99 pixel value of what we say, so we have here 331 pixel values, what we say, reduced pixels of reduced data, and from that reduced data we reconstructed the image, which is this one. This one is more precise, as you can see here, than the previous one, which is of 95%. Here we used a 99%. So this is pretty nice. So let's do an experiment quickly. If you want to just reduce the data into the, for example, 10 by 10, this will I will put here 100, and which is 10 by 10, and we reconstructed that data. So let me run each of that. So it's put in the data. Okay, it's 100 component. This is reduced to 100 component, which is oh, nice way to okay, it is reduced to, as you can see, here's the pixel values of 100 by 100. I think not 100 by 100, it's 28 by 28 itself, constructed from. So this is the principal component analysis of the MNAST data set. Here we showed that same thing of breast cancer data set, and if I quickly run this, so here we have a 300, it's not 300, 30 dimension is now projected to the 10-dimensional space, and we get variance of approximately equal to 95%, if which is of course a attribute of the PCA object, and which is named with a explain variance ratio. And if I quickly want to, okay, this is not connected kernel, so I will show it to you later in the upcoming videos. We already passed about we have actually passed about 39 minutes. Okay, so that's it for now, guys. I hope you are doing well, so keep learning. I'm also learning at the same time, and that's it. So let's close our video. Before closing, I want to request you, if you haven't subscribed at please subscribe and hit the like button if you want the if you think the content is appropriate, or what we say precise. It's not precise yet, but I'm trying very hard to fixing some glitches or some technique of showing the code. Or so I think I don't want to what do we say I don't want to record a video which is pretty good. Actually, I don't like I don't like a scripted thing, so I won't always wanted to do live streaming live. So if we in this world of programming, if you want to actually learn something, don't 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 copy the code as it is. Don't what we say or don't try a scripted thing of a program which is predefined. Don't put the predefined thing. So as of now I'm putting the predefined thing actually right now, which is a code which is actually written by me to show you quickly what's going on. But after some time I will code myself. I will debug the errors. I will execute the what do you say I will evaluate the errors in front of live streaming itself. And right now I'm facing some glitches, so thank you once again. Please subscribe, share the video, share the live stream as much as you can, and once again thank you so much. Good night. Thank you.